The first thing you picked up today is a little reading. The video last night was about something called water potential, and so water potential is not in your textbook, so I copied a little excerpt about what water potential is as a frame of reference for you, so you can refer to that since it's not in our textbook. So that is for you and your reference. The next two things here we're going to talk about in just a minute pertain to the second part of our lab where we're going to use potatoes. And so we're the one that says Osmosis Challenge Part 2 and dilution of stock solutions. So we're going to go through this together and address that today in class. And then the last one says AP Water Potential Sample Questions. There's 7 problems based upon the information that was in last night's video. And so if you look up here about what's due and so on, remember that tomorrow the dialysis tubing lab is due, but also when it says here water potential problems due Friday, that's these here. So these 7 are applying the stuff from the video last night, and so therefore, so you might want to note on that that's due on Friday. So let's take a look at the 2 that you picked up here and it pertain to the lab. And so I want to focus on the dilution of stock solution real quickly here. So let's look at that. And as an intro to that, actually let's look at Osmosis Challenge Part 2 first, and then we'll look at the dilution of stock solution. So last night's video was about water potential. Water potential is the potential for water to move from where it's at to another place, all right? So there are 2 things that play a role in where water is going to move. Can somebody give me one thing that plays a role in if water is going to move from that solution to someplace else? Give me one thing as well. Pressure. All right, so if you put pressure on that solution, does that increase or decrease the likelihood of that water to move to another place? It increases it. Pressure always increases that potential. The second thing that plays a role in if water is going to move from one place to another is what? Solutes. Solutes, when you add solutes to a solution, what does that do to the potential of that water to go from one place to another? Decreases it, because what happens when you add solutes? It decreases the water concentration, right? And so as the water concentration decreases, remember water flows from high to low concentration, you're decreasing the likelihood that water is going to have a high concentration higher than the other solution and move from one place to another. So those are the 2 things that play a role really in the direction in which water flows, in the diffusion of water or osmosis. Now let me ask you this, so what we would say then is that instead of saying water flows from an area of high to low concentration, it's more correct and all-encompassing to say water flows from a high water potential to a low water potential, because that takes into account not only the concentration, but also pressure. Okay, so that's more technically correct. So let me ask you this, if a cell is in an isotonic solution, what is true about their water potentials? The cell is in an isotonic solution, what is true about their water potentials? Annie?
They're the same.
They are the same. The water potential would be the same. Remember, isotonic, that cell would neither gain or lose mass, and that's because the water's going in and out equally, so that means the water potential would need to be the same inside and outside of the cell. So what we're going to do in the second part of the lab is we are going to design an experiment to actually figure out the water potential of living cells, and we're going to use plant cells, and we're going to use potato. All right, so so that's what I wrote up here on the Osmosis Challenge Part 2. And so the materials that I'm going to give that are available to you are, all right, potatoes, of course. All right, so I have a big bag of potatoes here. All right, and you're going to have cups. So what I'm doing is showing you the materials. You are going to, you're going to use these materials today, and knowing what you have available to you, you're going to design an experiment to figure out the water potential of potatoes. So you have the cups, You have potatoes. The potatoes, you also have this thing called, right here, a cork borer. All right, looks like this. A little guy that sticks in the middle here. So what this is a handle, and it has a cylinder, and you can look through, there's a hole on either side. All right, so that's what it looks like. What you're going to do is use potato cells. You're gonna get a potato. So this is your whole potato right here. We don't want to use the skins because we're gonna in our experiment talk about osmosis and water movement. And so we want to cut. So you're gonna cut a slice of potato like this. Cut off the ends. So what you have is a little disc like this, where the skin is around the outside. This part and this part underneath there, sitting on the table or whatever, has the fleshy parts. So what the cork borer does is allow you to get uniform pieces of potato by, if you have this on the table, you can take the cork borer and stab your potato, pull it out, and inside there you'll have a little cylinder, little round little french fry, all right, inside of there. And so that's where this little nifty guy comes in handy. You go like this, and it pushes out, and then you'll have a little potato cylinder, and you get uniform pieces of potato. All right, so you want to make sure to get it so that there's no skin on it, so it's all the fleshy cells, so the skin will interfere with osmosis. So you have the potatoes in that. Then it says there's 6 different solutions you have. So here it tells you distilled water, all right, so you have that's 0 solutes. But you also are going to have different molarities of sucrose, 0.2, 0.4, 0.6, 0.8, and 1 molar sucrose solutions. And notice it says 100 milliliters of each. So you have that available to you, increasing concentrations. You have a graduated cylinder that measures, I don't have one up here, but I'm hoping you know what that is. It measures milliliters, so you can measure volume. The balances are the same 2 balances we used for the first part of the lab. And these massing cups, these guys look like this. Here, these cups right here. And what they do is you can set on the scale. So if you get your potato cylinders, the scale, I'm not sure how familiar people are with the scale, but on each electronic balance there's a button that says tare. And so what you can do is, before I put my potatoes on there, I don't want you to put the potatoes on the scale directly. So you put your massing cup on there. The massing cup has a mass, so you're going to see that go up. But if you hit the tare button, what that does is make it read 0, so it's like it's not even counting the mass of the cup. Then you can put your potatoes in, and then it goes up, and it's just the mass of the potatoes. Then you can take your little cup back to your desk, okay? So that's also what you have available there. All right, so those are the materials that you have. And you are going to use these materials to design an experiment to figure out the potential of the water potential of potato cells. Before we do that, though, I said here that you have 0.2, 0.4, 0.6, 0.8, and 1 molar sucrose solutions available to you, and you have 100 milliliters of each. You are actually, the first part of the lab tomorrow is that you are actually going to make these solutions. All right, so this is what this sheet here is about, the dilution of stock solution. All right, so I'm going to look at this real quick, and I'm going to go through and I'm going to show you what to do. It's not hard, all right, but you need some instruction. Now, in chemistry, depending upon, I think, the class or what chemistry you had and what teacher you had, you may or may not have learned the equation, and this is our equation on the AP Bio equation sheet. It says C1V1 equals C2V2. In chemistry, you learn it as M1V1 equals M2V2. Does it sound familiar to some people? Some people, not to others, right? This is what I thought was going to be the case. All right, so it's not hard. It's good news that it's not hard. So I'm going to teach you how to do this and how to apply this to tomorrow's lab. So let's take a look at this, and I'm going to model this with you. All right. So, go ahead. I'm just going to have you read this intro here for a second, and then we'll talk about it. Because this just is the introduction and gives you an example, and then I'm going to go over it with you to explain. So just look at that for a second. So when we dilute something, what this means is, let's say you're given a 2 molar solution of sucrose, but you only need a 0.5 molar solution of glucose. So therefore, obviously 2 molar is greater concentration of solutes than a 0.5 molar. So therefore, it's a way to figure out how much of the stock solution do I need and how much to dilute it to make it the correct concentration. So when we look at this particular example here, so we have this equation C1 V1 equals C2 V2. So the ones are like your initial, what you start out with, and the twos are your final, what you end up with. And it tells you that C is the initial concentration, so that's in molarity, and then the final concentration, and V is your volume. And so we're going to use that in milliliters. All right, so these are the units that we're going to use. All right, so the example, if you dilute 174 milliliters of a 1.6 molar solution of lithium chloride to 1 liter. So I'm going to change this because we said that we're going to use the units, milliliters. So 1 liter is how many milliliters? Anybody know how many milliliters are in a liter? 1,000. 1,000 milliliters in a liter. All right, so that's 1,000. What's the new concentration of the solution? And so what you're given, so if I look at here, so I'm diluting 174 milliliters of a 1.6 molar solution. So that's what I have. All right, so this is my original concentration, so that's my C1. And this is the volume that I have, so that's my V1. So that's what they did here, C1 and V1. I always know when I'm looking at a problem, I just underline it and kind of label what I have, what I'm given. And we're going to dilute it to 1 liter or 1,000 milliliters. That's my C2 or V2. That's my V2, that's my final volume. I want 1,000 milliliters. And it's asking you what's the, if I dilute that, so what does that mean? What that means is if I took 174 milliliters, so I have 174 milliliters, all right, of a 1.6 molar solution, and I dilute it, so I'm adding in water to bring it up to my final volume, which is 1,000 milliliters. So I'm adding in water, bringing that up here. Is my concentration still going to be 1.6? No, it's going to be way less than that, right? So that's what it's asking, what is the new concentration? What is that? So that's my C2, and this is what I'm solving for. So what would I have in that final beaker? All right, so therefore, you can plug in your numbers, and so in this case here, we're going to use milliliters in the lab, and so I'm going to, again, change this to 1,000 milliliters. All right, so then you can solve this, because they changed it to a liters, but I'm gonna have a switcher because I want to be consistent with the lab. And so here's my equation. So I manipulate and I'm gonna solve for C2, so I divide both sides by V2, and so therefore this is now my new equation, solving for C2. So I plug in C1, so C1 was 1.6 molarity. V1 is 100, we're gonna put 174 milliliters. All right, you get the same thing. And then your V2 is, they put a 1 liter, we're gonna use the milliliters as a unit of measurement. And so therefore, we multiply this, divide by this, and our C2 is 0.28 molar concentration. So now I have, what I would say is I have 1,000 milliliters of a 0.28 molar lithium chloride solution. All right, so that's what I have. All right, so I've diluted that from a Scotch solution that was more concentrated. All right, so what I'd like you to do is apply this to the next question, please. So see if you can set it up. What do you do?
I got the
Okay, that's okay. For milliliter? No, no. Depending upon country. Alright, so either one, you could do L's lowercase or uppercase. Alright, so let's go through this problem together. So, asks you, tells you the stock solution of sodium fluoride is 1 molar. Alright, so my stock solution, that's my beginning solution. So that is, and that's the molarity, so that is my C1. And then it says you diluted it and made 250 milliliters of a 0.5 molar sodium fluoride solution. So therefore, this is my final volume, so that's B2, and this is the final concentration of that, so that is C2. What was the volume of the stock solution before your dilution? So how much of the stock solution did you dilute to get it to 250 and make it 0.5? So therefore, I'm looking for B1, right? So that's what I'm solving for. So my equation B1 C1 equals C2 B2. I'm solving for B1, so I manipulate this so that C2 B2 divided by C1, 1. And so that is my equation. So now I plug in and solve for B1. So I take C2, which is 0.5 molar. I take B2, which is 250 milliliters, which is 0. And divide it by C1, which is 1 molar. So notice the molars cross out, those units cross out. So I multiply this together, so it's really 250 multiplied by 0.5, because you're just dividing it by 1. And so I get 125 milliliters, all right? So they took 100, so what that means, like, so conceptually, is they took 125 milliliters of that original 1 molar solution and diluted it with water up to 250 milliliters. So they poured in water, alright, so they added water and diluted it up to 250 and to make your 0.5 molar solution. Alright, so that's what they did. Alright? Alright, if you haven't already, do the second one. Some of you may have already gone on to that, some of you may not have, so.
That really gets their best in state. What's your favorite kind of
Alright, you guys, let's go over this one here. Alright, so, check it. So by diluting a stock solution, you made 2 liters, and so we're going to change that when we do the calculations to milliliters. So that's your B2, that's your final, because you already made it, of a 0.2 molar solution, so that is your final volume, so that is your C2. Your stock solution had an original volume of 500 milliliters, so that is your B1. So then it says, what was the original concentration of the stock solution? So the original concentration, I'm solving for C1. And so again, C1 B1 equals C2 B2. I am going to solve for C1, so I'm going to change the equation here, divide both sides by B1. Alright, so that's what it looks like. my numbers, and so C1 equals, C2 is 0.2 molar solution. B2 is 2 liters, so I'm gonna change that to milliliters, so I'm gonna make 2,000 milliliters, so my units cancel out. Divided by my V1, which is 500 milliliters. And so, notice here, milliliters cancel out, so I'm gonna end up with molarity as my units. So you multiply 2,000 by 0.2 divided by 500, and at the end, you should have a 0.8 molar solution. Alright, and that is your original volume. So they took that and diluted it. Alright, so that's that. Any questions on that? Now we're going to relate it to our lab. So maybe turn it over. And we're going to give you a problem that is we're going to apply to our lab. So let's say, I'm going to say it out loud as I write it. You have a stock solution of a 1 molar sucrose solution. So it's okay. So you've got this a whole bunch of this 1 molar sucrose solution. My question to you is, how much of it do you need to dilute with water? To have 100 milliliters of a 0.2 molar solution. Start out with 1 molar. So how much do I have to dilute? How much of the original solution do I need to add water to 100 milliliters to make it a 0.2 molar solution? So let's go over this together. So your stock solution is a 1 molar sucrose solution. So 1 molar, this is your original concentration. So 1 molar is your C1. That's what you start out with. All right. How much of it do you need to dilute with water to have 100 milliliters of a 0.2 molar solution? That's what you want at the end. So this is your volume at the end. So this is B2. And this is your concentration at the end, what is it, C2. So they ask you how much of that 1 molar sucrose solution do I need to dilute with water. So what this thing is saying, I'll draw it here in a picture again, is how much 1 molar solution do I need? How many milliliters do I need to dilute with water to bring that up to 100 milliliters so that my final concentration is 0.2 molar? Alright, so therefore what I'm trying to figure out is how much of that, so I'm trying to figure out how much of it you need to dilute it is going to be my V1. I'm trying to figure out what is that original volume that I need. Alright, so that's how to think about that problem. So C1 V1 equals C2 V2. I am solving for V1. Alright, so I'm going to change the equations here. So I'm solving for V1 and plug in my numbers. So V1 equals C2 is 0.2 molar. V2 is 100 milliliters. Divided by C1 is 1 molar. Alright, so therefore I cross out my molar and molarity. I'm left with milliliters. So V1 equals, what did I end up with? 20 milliliters. Alright, so what that means is, so it's my volume. So out of my stock solution, I have to measure out, let's say I had a whole liter of 100,000 milliliters of the stock solution. Obviously, you're not going to dilute 1,000 milliliters to make 100 milliliters of a 0.2 molar. So therefore, this is saying out of your big stock solution, measure out 20 milliliters of it, then add enough water to bring it to 100, and you end up, instead of a 1 molar solution, 20 milliliters of a 1 molar solution, you end up with 1,000 milliliters of a 0.2 molar solution. Alright? And so, back on this, let's see, the sheet here, this is what you're going to do. The first thing that you come, first part of your lab tomorrow is you are going to use that dilution equation, and you are going to make these sucrose solutions. What I am going to give you, you are going to have a stock solution in a cup of a 1 molar solution, and I'm going to give you probably a little over 300, maybe about 350 milliliters of a 1 molar sucrose solution. And you, out of that 350, you have, and you're going to have distilled water. You're going to dilute it. So to make a point, I just did the first one together with you. So what you would do is you would take 20 milliliters of that stock solution, put it in a cup, add 80 more milliliters of water, and you end up with 100 milliliters of a 0.2 molar solution. Alright, so then the next one, you do the same thing except C2 is 0.4. Does that make sense? Yes. Alright, and 0.4. Alright, so and if you have any questions with that, I will be obviously there tomorrow to help you. Alright, so with that being said, so I want to point out that actually you're not given 100 milliliters of each, you're going to make 100 milliliters of each from your stock solution, alright? So you're going to have 100 milliliters of, you're going to have distilled water, but then you're going to make your 0.2 through 1.0. And so now what I'd like to do, you to do is in your lab groups talk about what you could do with these materials, with these solutions, and with the potatoes, and mixing the potatoes, and so on, to try and figure out the water potential of the potatoes. Alright, so I'm going to let you brainstorm for a little bit. I'll walk around. I can kind of hear head you in the right direction. Use your knowledge about what we've done with osmosis and diffusion in the last couple days with the lab, with the sample problems, like in the challenges. See if you can figure something out.